recording. Yeah, it's start now. Okay. Good morning, everybody. I'm very happy to be here with Salome. Salome, can you hear me?
Yes. Hello.
Thanks. So Salome is also a student in the data engineering major. Sorry, I don't have my webcam. I don't know why. Can you see me now? Yeah. Okay. So Salome is here to talk to you about the importance of math in her own experience. Okay. Yeah. So Salome is part of the first group of students of the data engineering major at EPF. She's right now in Germany, working on different things of deep learning. She recently joined a tech company. So, Salome, can you please maybe tell some things that you in your experience are important? What's the place of mathematics for your own work? Is it, I don't know, any type of suggestions you may give to your colleagues? And also, if you others have questions, please ask to Salome any question. Okay. So please. Do you want to talk first, Salome? Just to present quickly.
Yes. So, I'm actually okay. Yeah. Hello, everyone. So I don't know how to start, but maybe let's start with the how I discover mathematics and machine learning and how I actually really liked it. So my first internship in Catra was in a research center in Berlin, where I am now also. And I learned I actually discovered let's say the first phase of the most important aspect of mathematics, which was but for me at least, in deep learning, for example, it was like the backpropagation. I think you will see later, backpropagation, like concept, I would say, theory, and in neural networks. And then I learning step by step, and I think. I don't know, but like, did you switch a bit the program? Like in fourth year, you start with the probability or
Yeah.
machine learning?
Yeah. So this year we start with probability. Last year we start with linear algebra. This year, since we will have another teacher who is going to be with us this year, he will take the linear algebra part. So since he's starting his lectures later, I decide to start with probability.
Okay. The probability that we saw with you last year was like for me really amazing, because the book that we studied with was really full and has exercises, and like I would actually suggest to do the exercise, or at least to try to do it. And like the old concept of machine learning, for me it's a bit blurred for a lot of person, and mostly when you start to learn, like it's still a bit blurred for me, like a lot. But at least there's some concept that I can feel to understand, and then I'm bit more at ease maybe. And like the data science, for what I understood and what I actually, with the people I met, is like the fusion with mathematics and coding. So it's literally a translation to mathematics concepts into coding, and then making like a system, like like an algorithm who can do some like, I don't like to say AI because it doesn't really exist, but some like a machine learning concept, I would say. And yeah, I don't know if I got too much.
So in your experience, do you think when you was in the fourth year, so just 2 years ago, it was your impression of mathematics, it was underestimated, or it was right, or so what did you discover after this 2 years of study here?
So it was really underestimated. I thought I was going to data science, and I thought it would just be like coding, and I was a bit afraid of it. And I first needed maybe like concrete understanding, and I didn't thought that like the math could actually bring it. And the amount of math is really necessary to understand. I feel like data science, and what is a bit maybe not inside the black box, but at least like the major concept of data science and why we do data science. And yeah, I'm actually really happy to do as much as.
Okay. Do we have questions from the attendees here? Just jump in the occasion, because it's not very common to have some students from the who have the time and they want to exchange their own experience. Any questions to Salome? Yeah, Ivan?
Yes. When you say you use maths, so yes, hello. When you say you use math, because, well, we obviously will have two main branches of math, but which one do you use the most?
I would say statistics, but like it's not at all the statistic I thought it would be. Like we go way deeper into the concept, and it's not really what we like. It's, for me, the math that we see right now are more concrete and more interesting than the old math that we saw before in third year and second year, first year of engineer school. Like it's
Okay, thanks.
I think we have another question. So from Zekun, what was the book you're talking about? The book is the title is Mathematics for Machine Learning. The author is Weisenroth. I will put it on the chat. Okay. Any other question to Salome? Albin, do you don't have any questions? Yeah, the answer is yes. And any questions to Salome?
What do you do exactly in your job now?
So I like I haven't started yet, but I know what I'm gonna do. I'm starting like tomorrow, I think, and I'm gonna do some clustering. So I'm gonna try to find some with machine learning, you can find some, like, gather some information together with probability, for example, in text with NLP or in NLP concept, or for me, it's going to be geolocalization, location. So, and I'm going to also work in image recognition. I'm going to do a little bit of everything because my the company I founded, it's really nice, I think, for a first internship because they have started to do machine learning just a year ago, and together, so, like a small team together of data scientists with really different profiles. So we have like a machine learning teacher in Prague, like software engineer, IT person, a little bit from everywhere, even a guy who did biology, I think, and converted himself to data science and software programming. So it's like, yeah, we're gonna work on a little project and with a lot of like a panel of a lot of different type of machine learning, I would say.
Okay.
But for example, I do this, but in my class, like, people doing really different things. Like data science leads to really different things, and I think the math are always used the same way, but it depends of like what you do.
Okay, thank you.
Thanks. So any other last question before Salome leaves? Well, I think that's all. Thank you very much, Salome.
I
Yeah.
had a question, but it seemed that it doesn't send. My question was, when you're saying that the math now are more concrete and useful, are you referring to Bayesianism?
Are you what?
Are you referring to Bayesianism, like to apply in your real life concepts of probability and statistics that you learn from machine learning?
In my real life, like in my professional life, yes. But
like
in
to take better decisions, even in your
yes.
life?
Yes, or for example, like my P5 was a NLP, so natural language processing. So it's let's see, deep learning and machine learning with the text. And it was from like a survey. We had to take some data from it and try to find like some needs of the people wrote inside the survey. And to do this, for example, I use like a n-grams concept, which was a probability and frequency concept in mathematics to like it's just I translated into computer language, and then I could do some statistics and find the probability of certain words, or like this is actually working like this a bit in general, like machine learning or I don't really know how to say, but like most of the time it works with probabilities and frequency, and you can extract a lot of information from it, or I don't know. I don't really know how to explain, but yeah, so it's really helpful. It's for me the base of what we like everyone has done for data science.
Okay, thank you very much.
Well, thank you very much, Salome. It was really nice to have you with us. Yeah, as usual, if you need anything, just send me a message or something, okay?
Okay, I hope I was useful.
Yeah. I think it was. I think also maybe they for them it's too early just to
Oh, okay.
being in conscience of what that means, and until you don't experience something, it's quite difficult to have a good idea of something. But yeah, I think they will remember this meeting, and maybe in some months that will be much more clear for them.
But I don't know you guys, but if you want also to contact me for any question later, you can through Mayo or to contact me for, I don't know, for help. Okay.
Okay. So we'll start the class now. Thank you very much, Salome. See you soon,
Yeah.
and good luck for the work.
Thank you. Bye.
Okay, so do you have any questions about the things we did last time, just before starting the next section? Okay, I guess that means no. Okay, that's good. Last time we talked about the geometric distribution, I think, and just as a small thing, where's my, yeah, it's here. Okay, the pen is there. Okay, so just to remind you, the geometric distribution, why is this like that? Okay, the geometric distribution is the following. So we have this definition here that says that a random variable x, taking its values in the positive natural numbers, okay, taking its values in the natural numbers without zero, okay, and this is just n star, okay, without the zero, and satisfying that the probability of x equals k, it was just convex combinations of p. So this was p times 1 minus p power k minus 1. Okay, and p, of course, was a number between 0 and 1, possibly it's just a parameter, is the geometric random variable x with parameter p. Okay, and we say that x follows geo of p. Okay, so this is x follows the geometric distribution of parameter p. Okay, depending on the value of this number p, the actual graph you have, the actual graph of the density will be a little bit different. Okay, so let me show you. I don't remember if I share with you. Okay, the visualization of the density of the geometric distribution. So I want the geometric distribution of parameter p. Okay, for that geometric distribution, I want the probability distribution function. So this is just this plot here. Okay, I want this plot for yeah, this is actually in the I make this bigger. Okay, so you have the plot of this thing is k minus 1. Yeah, so that was good for x from 0 to 8. And p is just a number between 0, let's say 0.1 and 0.99. Okay. Oh yeah, I actually want the discrete plot. Yeah, so that type of things. Okay, so so in you can see the shape of the probability distribution function. So it's sort of decreasing function. It's related with the exponential one. You will see later why. And here the value of the parameter p makes some changes. Okay, for example, here for the parameter p equals 0.4, the function is decreases more rapidly. Okay, and for a slower value of p, then you get a decay which is lower. Okay, at infinity. In any case, the function tends to 0 as k tends to infinity, but it's going to different speed depending on the value p. Okay, good. I don't remember if we talked about the expectation of the geometric distribution, but if I didn't, well, here it is. So we have a theorem that says that if x follows the geometric distribution of parameter p, then the expectation of x is simply equals to 1 over p. Okay, so if p is smaller and smaller, then the expectation is bigger and bigger. Okay, and that also confirms the behavior we saw just before. Yeah, so this is important to know. And maybe most important than this theorem, much more important, is the fact that geometric distribution is memoryless. Okay, so here we have a theorem that says that the geometric distribution is memoryless. What does it mean? The fact that the geometric distribution is memoryless. Well, it means that if you have here a random variable t, okay, so let t follow a geometric distribution of parameter p. P, of course, is something between 0 and 1, open interval. Then for any integer k0 bigger than 1, okay, the probability that the random variable t takes the value k plus k0, given the fact that t is already bigger than k0, is simply equals to the probability that t equals to k. Okay, so here you can see that we have a conditional probability, and this conditional probability looks at the event t is bigger than k0. Okay, the proof is quite simple. Okay, so it's simple enough to just prove it here. Proof. We have to compute what's the probability that t is bigger than k0. Well, this is simply given by the sum of k equals k0 plus 1 up to infinity of the value of probability. So the probability that t takes the value k. Okay, that's quite simple. Now, this probability, since t follows a geometric distribution, is p times 1 minus p power k minus 1. So this is equals to the sum of p times 1 minus p power k0, not k minus 1, sorry, k minus 1. Okay, and actually I can factor this as follows. Okay, you take the power you need and you take it outside. So this is equals to p times 1 minus p power k0. Okay, so you take the first step, the first power, and you simply factor the expression by that, times then the sum of 1 minus p power n. And this sum runs from n equals 0 up to infinity. Okay, and this is actually interesting since we know a simple expression for this this last sum here. So this is equals to p times 1 minus p power k0 divided by 1 minus 1 minus p. This is a traditional formula you know since you were in high school, I think. It's a geometric sum, okay? And this is simply equals to 1 minus p power k0. And this is exactly what we need to conclude the proof, since the probability that t equals k0 plus k, given the fact that t is bigger than k0, is by definition, okay, equals to the probability that t takes the value k0 plus k, and t is bigger than k0 divided by the probability that t is bigger than k0. This is simply the definition of conditional probability. And finally, you can simplify this expression as the probability of t equals k0 plus k. Okay, since this is redundant. Okay, this information and this one, they are redundant, so this is simply the probability that t takes that value, k0 plus k, divided then by the probability that t is bigger than k0. And finally, we can just replace those expressions by their actual values. So this is p times 1 minus p power k plus k0 minus 1 There we go. And this thing divided by p, no, sorry, 1 minus p power k0. And if you simplify this thing, you get p times 1 minus p k minus 1, you know, and this is just the probability that t takes the value k. Okay, so that's the proof. And if you summarize the thing, so just it's just a computation, it's basic algebra. You conclude with this theorem. Okay, any questions about that proof? No. Okay. So,
yes. Can you repeat about the redundance at the top of the conditional probability, please?
Yeah. So here you say, okay, the event t bigger than k0. Okay, so if you draw an axis, let's say we are here, that k0 is somewhere like there, and this yellow event is t is bigger than k0, so I'm here. Okay, now the event t equals to k plus equals k0 plus k is somewhere here. Okay, k0 plus k. So if you intersect the yellow one with the brown one, what do you get?
I don't see what you draw because there is a lag time between what you say and what you draw.
Oh, really? No, I'm sorry for that. Do you see now the?
Yes, I saw a dot, an orange dot on the yellow line. Is that it?
Mm-hmm. Yeah, that's the thing. So what do you get if you intersect the yellow line or semi-line with the brown dot? What's the intersection of those two sets?
The probability of k. That t equals k. No?
I mean, what's the intersection between the yellow line and the brown?
Only the k0 plus k.
Yeah. Okay. So that's why you pass from this first line to the second one, and you say that numerator, those numerators are equal. Since the probability of the intersection is just the brown one, so I get the brown.
Okay. Thanks.
Mm-hmm. Any other question? No? Okay, so I'm sorry for the lag. I don't know why the network is having troubles in those moments.
For me, I don't have any lags.
Ah, okay. Well, good. Okay, any other question? So if you have questions, just stop me, okay? It's difficult to me to see the chat at the same time, so if you have any question, just ask. Okay, so maybe I can tell you when, well, maybe later. I will tell you when you have.
Sorry?
Yeah?
Do you have an example of this theorem in real life? I don't understand why we this theorem.
Yeah, so this theorem tells you something about the memory. Okay, so memory implies that the past affects the future. Okay, and here, okay, the past is wherever that happened between 0 and k0. Okay, so this property of this type of random variables is something that may be true or not depending the situation. Okay, I just prepared for you a couple of exercises you are going to do, and if you can just wait a little bit to see examples of applications of all the random variables. Okay, but if I can say something very fast, is that this will be the case also for Markovian hypothesis. The Markovian hypothesis says that the future is only affected by the past through the present moment. Okay, so all the present steps don't affect the future. But yeah, just be a little bit patient to have an application of that.
Okay, thank you.
Any other question about the proof? No? Okay, so what's the idea of those computations? You have to be able to think about those distributions at least in a geometric way. What does that means? You have to see in your head what's the shape of the PDFs of those functions. Okay, the probability distribution function. If you remember, it's the pi function, and it tells you what's the probability to be at one precise value k for each distribution. Okay, so for the moment we saw the Bernoulli distribution, we saw the binomial distribution, the geometric distribution. We compute some of their expectations, their variance. For the moment, we are just giving a lot of different types of variables and compute some of their properties. And the idea will be later to exploit those properties in specific cases. Okay, I know it's too early to give you full examples, so just be a little bit patient. You will be. It will be much more clear in some lectures. Okay. Okay. Now, what can we say? Well, if you want to compute the variance of this distribution, you can. If not, you will have a list of a table with all the values computed. So you don't have to know them or memorize them right now, but at least you will be able to find where they are, those values. Okay, so and now we are going to talk about the Poisson distribution, then the multinomial distribution, and then we can finally start talking about the conditional expectation. Okay, but I need to talk about those laws before, just to have them in our toolbox. Okay. Yeah, so we have the Poisson distribution. Poisson distribution. So if you consider a random variable x, taking its values in the natural numbers, okay, so definition, let x from omega to n be a random variable taking its values in the natural numbers, taking its values in n, such that for any k bigger or equal than 0, the probability that x equals k is simply the exponential of minus theta times theta power k divided by k factorial. Okay, so this is the Poisson distribution, and it's denoted by p. Well, it depends on people, but for me, I will say that x follows the Poisson distribution of parameter theta. Okay. Again, for this distribution, you will have a full example in the exercises. Okay. Now, what's the shape of a Poisson distribution? So here you can simply have the graph. Yeah, like this one. So here the parameter theta, well, here it's called lambda, it's the same, is 5, 10, or 20. So here plot legends expressions. So when theta is equals to 5, we have this blue curve. And when theta increases, look, you have a translation to the right, and the variance increases. Okay, so we expect that the mean and variance of those Poisson distributions depend on the parameter theta. And just look at this. Yeah, so if you ask for the mean of the Poisson distribution, it's lambda, so it grows. Well, here for my notation it was theta. The mean of the Poisson distribution is theta, so it grows linearly. And if you ask for the variance of theta, is also theta. Okay, so you have both growths linearly, identically to theta, as theta changes. Okay, so again, you will have the table with the values, but it's good to being able to compute them. Okay, so it's very, very easy, but try to do it by yourself to confirm that you are able to just deal with the sigma notation. Okay, so the Poisson distribution, or the Poisson random variables, they have an interesting property, which is that if you have two independent Poisson distributions, Poisson random variables, the sum of two Poisson random variables remains a Poisson random variable, and the mean is the sum of the parameters. Okay, of course, this is not the case for the other distributions. If you add, for example, two binomial distributions, it's not a binomial distribution. Okay, geometric distributions, they don't satisfy the same property. So here we have a theorem that says that if x1 follows a Poisson distribution with parameter theta1, and x2 follows a Poisson distribution with parameter theta2, and most importantly, theta1 and theta2 are independent. Sorry, x1 and x2 are independent. x1 and x2 are independent. Okay, then x, which is defined as the sum of x1 plus x2, is a Poisson distribution of parameter theta1 plus theta2. Okay, now the proof is also quite simple. What do you need to verify? And if you are, I mean, this is your work, you have to prove this theorem. So you have to compute the probability of x equals k and show that this is actually equal to what? to the exponential of minus theta 1 plus theta 2 times theta 1 plus theta 2 power k divided by k factorial. Okay, so it's just a simple computation. I'm pretty sure you all will be able to do it. But if not, just try and ask me if you have troubles with that. Okay. So this is almost the last discrete distribution we are going to study. The last one is the multinomial. And so what do we have in our toolbox? We have Bernoulli, binomial, geometric, Poisson, and multinomial. Okay, so we have 5 discrete distributions. They are important to know. So again, take each one, verify that you're able to compute the expectation, the variance, and probably, if you want, remember the plot of the probability distribution function. Okay. Good. Now the last one. Where's the mouse? Yeah. The last one is the multinomial distribution. So we're talking about a vector. Okay, so in this case, x is not just a single random variable, it's a random vector. So you have x1, x2, x3, xn. Okay, random vector. And each of the random variables xi take their values in a space E. That means that xi is a random variable from omega to E. Okay, this is true for any I in the discrete interval 1, n. And pi will be the function from e power n to r plus, okay, is a function such that the sum for any x in e power n of pi of x equals 1. So this is again the probability distribution function equals 1. Okay. And what does it mean that it's a probability distribution function? Well, it's simply the fact that if you ask for the probability that your vector takes the value x, probability that the vector x takes the value of x, okay, this is equal to pi of x. Okay, so this is the PDF, probability distribution function. Okay, any questions at this moment? Okay, so
yes.
Yeah.
Are we going to see the equivalence between the different distribution, or it's not useful for the course?
The equivalence? What do you mean by the equivalence?
I mean, when a distribution can be approached by another.
Yes.
Like
a distribution can be approached by another one?
Yes, for example, the binomial, I think, when the parameter is higher than 30, something like this, it can be approached by uniform or something like this.
Are you talking about hypothesis test or that kind of things?
Yeah, I think so.
Yeah, we are not talking about this since we are supposed to know already this. So normally the students at the third year, they have some lectures on inferential statistics like hypothesis test and that type of things. Yeah. We are not talking about that type of things. It's not really important.
Okay, but are we going to use it? It was the question.
No,
okay.
Not at all. No.
Okay, thanks.
Yeah. Okay. That's pretty all about the distributions. Okay, so here for the multinomial case, each random variable can follow a different type of distribution. It's not necessarily the same, but the necessary condition is that at the end, the sum of all the probabilities P of X has to be 1, okay? But I don't saying anything precise about each random variable xi, okay? So the first one can be geometric, the second one can be Bernoulli or whatever, okay? It's not important to have the same. Okay, so I think that was all about the first chapter. Do you have any questions about this first big chapter regarding basics of probability? So that starts from the beginning of the year until now. Any questions on that? So normally those were basic stuffs. But if it was new for some of you, well, just feel free to ask. Okay. Good. We can continue now with the conditional expectation. This definition is very important since later, when we'll be later, I mean next year, when you will learn how to train different machine learning models, the conditional probability and the conditional expectation are quite important computations. Okay. Good. So conditional expectation. Oops. Is it going too slow or too fast or whatever?
No, it's okay.
That's okay.
Good. Okay. It's good to have a feedback. Yeah, so now we're going to introduce the concept of conditional expectation given a random element. This random element can be a variable or can be a vector. Okay. So let z be a discrete random variable, be a discrete random variable with values in E, with values in E. Okay, that means just that C is a function from omega to E. And let F be a function from E to R. Okay, so this function F allows you to consider any type of expression that depends on the random variable C. Okay, Now, let an event with positive probability. Let A be an event such that the probability of A is positive. That means it's not a zero probability event. Okay. Now, the conditional expectation of f of z given A, which is denoted by the expectation of f of z given A, okay, this is by definition equals to the sum for any small value z. Okay, I will try to make the difference from the capital letters from the others. So it's the sum of any little z of f of z times the probability that the value z equals little c given A. Okay, so it's almost the same definition as the classical expectation. The only change here is that you are conditioning the probability and the expectation by some event. Okay. Is this formula clear? Do you have any question about the formula? It's as usual, okay? No very big surprise. Now, if you have a partition of the sample space, okay, that means I don't have only one event, but I have actually a sequence of events that makes a partition of the sample space. So now, if AI for I in natural numbers, okay, I have a partition, is a partition. Can anyone maybe just remind me what a partition is? Who can remind me what's a partition?
It's a subset of a set.
Yeah, it's a set of subsets. But what's the characteristic? So a partition is, you partitionate something. You have a cake here, and a partition is a way of cutting the cake such that when you add all the parts, you get the cake entirely, and also those parts are not intersecting themselves. Okay, so that's very important. A partition is a disjoint union which is complete. That means that you recover all the space when you add the elements of the partition. Okay. Well, so if I consider a partition AI of the sample set, okay, the formula I gave before of the conditional expectation can be used to recover the expectation on the whole set. Okay, that means that the expectation of f of z, okay, without any conditioning, is equals to the sum here over any I in the natural numbers of the expectation of f of z given AI times the probability of AI. Okay, so this is just a consequence of the base formula of total causes. You know, the probability of an event that intersects a set of events is the sum of the probabilities times the conditional probability of being on each one of those subsets. Okay. Yeah, so that's the conditional expectation. Okay. You may want to compute some examples of that using any type of events. Okay. Yeah, maybe we can just try an exercise. Yeah, we may just try an exercise here. Let's say, okay, so this is an exercise for you. If Z is maybe the binomial distribution of parameters n equals 30, or well, n equals 6 and p equals 1, 4. Okay, so I consider this random variable z that follows the binomial distribution with parameters 6 and 1/4. And I have the event A given by z is bigger than 3. Okay, I have this event. You have to compute the conditional expectation, then the expectation of z given A. Okay. So take some, I don't know, 10 minutes to answer that.
Can you show once again the formulas?
Yeah, which one? The expectation?
Yeah.
Okay.
The expectation.
Yeah.
Thank you.
Yeah. Anyone needs? Do you prefer I put here on the whiteboard the exercise or the definition of the expectation? Well, I think this one is more useful. Okay, I'm going to take some water and I come back. I want some answers about this, okay? Okay, so is there anyone who doesn't know how to start?
I'll start with something, but I'm not really sure it was the correct way.
Okay, so you want to say something, that's right, like propose a solution.
I was just answering your question.
Okay, but do you so what are you doing? What's your starting point?
I start with to write the sum between z equals 3 to 6 of z and z, the big Z equal little z such that A. And after this, I wrote what was Z with the binomial law.
Yeah.
And I start to just do the sum.
Okay. Yeah, that seems good for me. Okay. So I can give you more time and then correct the exercise. Okay.
Okay.
So I want to know for the other, is this question difficult? Is easy? I want to know where you place with respect of the type of questions. I don't know, maybe Adrien, what's your point of view of this? Is it easy? Is it difficult?
Which Adrien you're talking to?
Sorry, yeah, Dubois, it's good.
Okay. No, I just need to remember the formula, but I started doing the same thing as Simon, so.
Okay, good. Okay, so I'm giving you more time to finish this, and please, if you have an answer, just put it on the chat. Okay, I can know you have finished. Okay. Anyone has the answer? Okay. And you don't have the answer because of what? Okay, so we have 88. I don't know. I don't actually know the answer. I have to compute it. But so I want to know, are you unable to give the answer because of what? So Yvan, please, or Arthur, or Audrey, can you please tell me why you don't have the answer? Where is blocking? No?
Yeah. I don't know if I can show you a photo. It would be quicker, maybe.
Yeah, you can send it on the chat, but you don't know why you are blocked. You know what's the?
No, I just want to explain my whole
reasoning. Yeah.
Yeah, quicker than.
Okay.
I'm just send it.
Yeah, good.
So.
Okay.
On the third line, I don't know how to compute the probability of 4 intersection with A.
Okay. 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 And is it the same problem for the others? Or is something else?
No, for me the problem was that I changed the variable a with the variable z, saying that it was z superior to k plus 3, but I'm not sure that is the right way to go.
Okay, good. Well, let's correct the exercise. Okay, so by definition, this probability here, maybe I can change the place of this and that. Oops. Yeah. So the probability, sorry, this expectation, as we said, is just the sum. Okay, it's the sum of z times the probability of capital Z taking the value. I think it's Arthur. I just got your microphone. Okay.
Oh, sorry.
So it's the sum of Z times the probability that Z equals to Z given A. So this is a sum over Z. Now, this probability is a conditional probability. So I can use the definition of the conditional probability, and this leads to the sum over Z times the probability of Z equals Z intersection with A divided by the probability of A. Now, A is the set of values bigger than 3. And what's the probability of A? That's the next question we have to answer. So the probability of A, this blue thing, Well, the probability of A is just the sum of the probability that Z takes the value K for K bigger than 3. Now, you know that this binomial distribution has a probability density function given by this expression. Okay, and if you remember, when we draw this type of expression, we get a curve like this, and from n+1 to infinity, this is actually 0. Okay, because the binomial coefficients here will be 0 if k is bigger than 1. Okay, so this sum here ends on n. So this sum is for k equals 4 up to 6. This is the sum for k equals 4 up to 6 of the probability that my binomial random variable z takes the value k. So as I know the expression of this probability, this is just the sum of k equals 0. Oh, sorry, k equals 4 up to 6. Yeah, so sum from k equals 4 up to 6 of k binomial kn times p, in this case is 1/4 power k, times 1 minus p, sorry, so that's 3/4 the power 6 minus k. Okay, now you can of course develop this little sum that contains a relatively small number of terms. Okay, so this is just k among 6. Yeah, so that n here is 6. 4 binomial for 6 times 1/k power 4, 1/4 power 4, sorry, times 3/4 power 2. 6 minus 4 is 2, plus 5, 6, 1/4 power 5 times 3/4 power 1, so just 3/4, and then plus 6, 6, 1/4 power 6 times 3/4 time power 0, that's just 1. Okay, so that's all. Now, if you compute this sum, okay, I have to take my calculator here. So I want the sum of binomial 6k times 1/4 power k times 3/4 power 6 minus k. Yeah, 6 minus k, and this sum runs from k from 4 to 6. Okay, so I have this numerical value, which is 0.037. Okay, so this is just 0.037. Okay, now we have the probability of A, and we need also the probability of Z taking the value Z knowing A. Okay, now the green one. The green one is that thing. Okay. And what do you get if you intersect Z with something else? Okay, so maybe put, oh, sorry. But in this other side, I have the intersection of Z equals small c intersected with A. Okay. What do I get? Well, it depends. I have two different possibilities. If Z is smaller or equal than 3, okay, the intersection is empty. Then the intersection is empty. Arthur, you have your microphone activated. You want to say something? No? Okay. And yeah, so in this first case, you get just the empty set. And what do you get in the other case? That means if Z is bigger than 3, then the intersection will be just Z, okay? Because the set of value is just Z equals Z. Okay, so this is the thing I get, and this is the thing I get. Is it clear for everyone? If you compute these two intersections, you have, I mean, if you compute this intersection, you have two possibilities. The first one is if the value of Z is smaller or equal than 3, or bigger and equal than 3. So here in the right is small c, okay? So I tend to use both letters, but it's a small one. Okay, so as a conclusion, what can be said about the probability of Z equals C intersection with A?
It's A.
No, the probability is a number.
Okay. Can we say just the sum of Z and the probability of Z equals Z between 4 and 6?
Yes. Yeah, exactly. So in this first case, the probability is just 0. And in this case, it's just the probability of Z equals Z, which is also known as Z among 6 times 1/4 power Z times 3/4 power 6 minus Z. Okay. And of course, you run the sum over the
Isn't it
values.
the probability of A?
A is not, I mean, the probability of A, okay, is the sum of those guys here, those green guys, from 3 up to n, okay? And yeah, I mean, yeah, you're right. So this, you're saying that the sum of this is the probability of A. The sum of P of Z equals Z from 4 to 6. Sorry, I don't know why my tablet is not responding correctly. This is just the probability of A. That's the thing you are saying, no?
Yes.
Yeah, you are right. That's true. But here, what do I need? You know, I need another type of sum. I need the sum of Z times this probability here depending on z and divided by p of a. So maybe what you are saying that is that this fraction here will simplify. No? I don't know if you are saying that, but yeah. Okay. Well, now I have everything I need to answer the question now. Since this is equals to, so just as before, we say that when z is smaller than 4, this probability here is 0. So we have 0 plus 0 plus 0. Okay. Now, from this moment, we will have 4 times the probability of z equals 4 given a divided by the probability of a. Does this make sense? So it's 4 times, where's my, yeah. So it's 4 times the probability of z equals 4 given a. Okay. So it's just the probability of z equals 4. Okay. So here is times the probability of z equals 4 divided by the number I get at the beginning, which was 0.037. Okay. Now plus 5 times the probability of z equals 5 divided by the same value, 0.037. From this, you can see that I can factor by 1 over 0.037, and the last value is 6. So plus 6 times the probability of z equals 6 divided by 0.037. Okay. Now, if you compute this actual value, I mean here I have p of c. Let me just put it inside the computer. Is binomial. What? It's the binomial of 6 among z times 1 over 4th power power z times 3 over 4 power 6 minus z. Okay, the little probability. And yeah, so what do I get if I have 4 times p of 4 plus 5 times p of 5 plus 6 times p of 6. I get 159 over 1024, so I get 0.15. Okay, so this is equals to, where's the pen? Here. So this is equals to 0.15 divided by 0.037. That's weird because this will be bigger than 1. Maybe I made a mistake before. How much is this? So the last result divided by 0.037, 4.19. That's not good. I made a mistake somewhere. Let me check where. Why the mouse is not working? Okay. Let's check. The mistake probably comes from this blue thing. Okay, so I have the sum of P of Z. Okay, so here this is just the sum of P of Z for Z equals 4 to 6. That's yeah, 0.037. No, that's good. That's good. No, yeah, it's good. No, it's good. Sorry, I was confused about the value. I was thinking about the probability. This is not a probability. This is an expectation. So this value is the good one. At the end, we get 4.19. Okay, so here at the end, this is just equals to 4.19. 4.19. Okay. Yeah. So I see in the chat there are some questions. No, it's not a question. It's Simon that says 4.05. It was almost that. It was 4.19. Okay. Okay. So is this computation clear? Is this too difficult or not? You know, the thing here is you have some information, you have some sets, and you have to translate them into practical expressions. So you say, okay, the expectation has this particular value, I mean, this particular expression here. Now, this thing is just a number. Yeah.
Sorry, can you show me again the answer, please?
Which one, sorry?
The last one, 0.419.
Oh, yeah.
Right?
Mm-hmm. You want to see the value, or you want to have the explanation of why is this?
Well, for me it was 4.05. Just like Simon, it doesn't matter if there's a little bit difference.
Well, it may be because I didn't took all the decimal things, but I think it shouldn't be. Let me check something. It shouldn't be very. If I take now the numerical value, I get. Actually, the true value is 4.12987. If I keep all the decimals, because if you take the rational expression, is just 318 over 77. So if you want the exact value is 318. Okay, so this is 318 divided by 77. That's the true value, which is approximately equals to 4.12. Okay, this is approximately equal to 4.12. So if you don't get 4.12, but you get 4 or something, the difference may be explained by just the fact you didn't took your computation using fractions, you know, like entire numbers. But well, the precise value doesn't really matter. The important thing here is, do you get all the steps we use to compute the value? Okay, so maybe I can explain it again. I'm sorry about the noise, but here, let me just close the window. Yeah, so we have different steps. The first step is you use the definition of conditional expectation. You see that you need to compute this brown thing here, which is the probability of z taking the value little z. given A. Then you apply the definition of conditional probability. It's just the probability of the intersection divided by the probability of A. And then you say, okay, we have to compute probability of A. The probability of A is the sum for P of Z equals K for K from 3, from 4 to up to 6. Then you have to remember what's the value of the probability for a binomial distribution. Okay. Once you have done that, then it's just a matter of computing this little sum and you get a value, which is, if you want the precise value, is, let me check, 77 divided by 2048. So here the precise value is 77 divided by 2048. Okay. Now that's the denominator of this expression. Okay. Now, what do we get if we consider the numerator of the expression? So that was the second computation on green. The green computation, you have to compute the probability of this intersection of those two events, this event and this event. So this event here depends on the actual value of Z. It will be empty if Z is smaller than 3. That implies that its probability is 0, or it's a sum of probabilities if we get a different value of than which is bigger than 3. Okay, it's just the binomial expression again. And as your colleague says, it's just a remark. Of course, if you add all those probabilities from 4 to 6, you get the probability of A. And yeah, so we have the value on the denominator, and we have just to compute the sum. Here you get 3 zeros because if little z is smaller than 4, you get zeros. Then you get from 4 to 6 real values, which are z times the probability of that, plus 5 times the probability of that, plus 6 times the probability of that. Okay, is it clear for everyone? Any other question? Okay, good. I hope this was a little bit clarifying the other things. Okay. Do you want to take a break, or we may continue as you prefer? Nothing?
We could take a break. Yeah.
Okay. Yeah, if you want. Yeah, so let's take some 15 minutes of break. Yeah, come back here at 4:10. Okay.
Okay, thank you.
Hey, are you there? Is everyone with us, or are you still taking the break? Good. Do you have any other question about the things we did until now? No? Okay. We may continue with the next notion. Yeah, so you know, the conditional expectation of discrete random variable z, just as I present you right now, given some other random variable, okay, is the expectation of z using a modified probability measure. Okay. We are going to talk more precisely about this later. But anyway, let's give a definition. Normally it's clear enough, I think. But tell me if you don't understand fully the definition. So definition, let x and y be two discrete random variables, taking their values in two countable sets, f and g. Okay, so taking their values on f and g respectively. So f and g are countable sets. Okay. Everything we are talking about discrete random variables is countable. Now consider the following function g and let g the function from f times g to the positive real numbers, non-negative or integrable, non-negative or satisfying, the fact that the expectation of the absolute value of g of x, y is finite. Okay. We are defining for any y in g. So for any little y in g such that the probability of y equals little y is positive. Okay, so that means that this event is a non-zero probability. Okay. And we are going to define psi of y. Okay, so this is by definition the following quantity. You remember when I say column equal, that means that I am defining something. So psi of y is the sum of any x in f, g of x, y times the probability that x equals x and given y equals y. And of course, there's the case that what happens if the probability of y equals y is 0? Well, in that case, you say psi will be 0. Okay. If the probability of y equals y is 0, then we just say that psi of y is also 0. Okay, so this quantity here is the conditional expectation of g of xy given y equals y. Okay, and it will be denoted by the following notation. Okay, so I can say here that this is the expectation of j of x y given y equals y. Okay, so I can denote this by this. And the random variable psi, okay, so psi, which is a function of little y, is a random variable. It's a random variable called the conditional expectation of j given y. Call the conditional expectation Okay, the conditional expectation given y. And it's just denoted by expectation of g of xy given y. Okay. Now, so this definition extends the first we saw to the general case of two random variables, a couple of random variables. Okay. And again, you will have some exercises to try to answer this. Okay, so that was all the thing I want to talk to you about the conditional expectation. Okay, so it's maybe a good moment to make a recap of all the notions you must know until now. Okay, so the first notion you may you have to fully understand, okay, is that one of sigma fields, events. That's the first thing. Then probability of an event. What's the interpretation of that? The conditional probability. Okay. Of course, the Bayes theorem and all the other type of results we saw regarding the application of Bayes theorem. Okay, the total causes probability. What else? Yeah, then we saw some random variables, expectation, variance, and the classical ones, Bernoulli, binomial etc. Binomial. Now we saw today the conditional expectation. Okay. And of course, everything we saw can be extended to vectors of random vectors, okay? When you have n random variables, and conditional expectation of couples of random variables, okay? So a couple is just a particular case of vector of dimension 2. It seems good for me. Any question about that? Is that clear? Okay, so now we can talk about something called branching process. Okay, anyone, maybe those who were in class prépa, you learned something about stochastic processes. Les processus de branchement, is it something that you have heard before? No? Okay. Okay, so this is new for you too. Okay, so we are going to talk about branching process. Oops. Branching process. In French, this is known as processus de branchement. Okay, it's a particular type of stochastic process. Okay, so the branching process is also known as Galton-Watson process. Okay, so also known as Galton-Watson process. Okay, and you know, Francis Galton was a relative of Darwin, and he was interested in the probability of survival of a given line of English peerage, and he posed the problem in a paper called The Educational Times in, I think, 1873. And the same year he proposed a solution, okay, a method to solve this problem, and it became very classic. And the elementary theory of branching processes is something that we have to study. And before going further on that type of things, we have to introduce a new way of seeing the probability, which is the generating functions. Generating functions. Okay. So when you compute probabilities, at least in the discrete case, you often need an enumeration of all the possible outcomes that realize a particular event. And generating functions are very useful for this task, and more generally for obtaining distribution functions of integer valued random variables. Okay, so we need to define the expectation of a complex valued function. Okay, like this. So you will see that actually it's the Fourier transform of the density. Okay, it's related to the Fourier transform of the density. Okay, so let X be a discrete random variable, DRV, with values in N, with values in n, and let phi be a function from n to the set of complex numbers. I know that you all have notions of complex numbers, but I want to know if our international students, do you already know what complex numbers are? Or I guess yes, but just to be sure. I think it was Melissa, no, who is the only international student, I guess. So Melissa, is this notation known for you? Do you know, you have familiarity with complex numbers?
Well, I saw them a long time ago, so in the moment,
Okay.
I remember.
Okay.
Yeah, we see probability like the first or second year in the university, and actually I'm in the 5 technically, so I don't remember.
Okay, good. Well, if you already study complex numbers, that's fair enough for the things we are going to do. And if you need anything, of course, you feel free to ask. Okay. Now, I have this complex function. I mean, this function that goes to the set of complex numbers, and of course, this function can be decomposed into a real part and imaginary part. Okay, so the expectation of phi of x will be just, since the expectation is linear, the sum of the real part and the imaginary part. So that means that the expectation of phi of x is equals to the expectation of phi in the real part of x, sorry, capital X, plus I times the expectation of phi imaginary part of x. Okay. And of course, I am supposing that those expectations are well defined and they are finite, but that's essentially the thing you need to know. If I have a value that goes to the complex numbers, then the expectation is just the expectation of the real part plus I times the expectation of the imaginary part. Well, now I can start with a definition of the following object. What's the generating function of J? So let x from omega to n discrete random variable. Its generating function, and that's the new concept, it's generating function, often abbreviated as FG, generating function, GF, sorry, generating function, is the function G, which is defined on the set of the disk of 0, 1, okay, closed. So what is this? What is this set? This is just the set of complex numbers with modulus smaller than 1. So this is just the set of Z in C such that modulus of z is smaller or equal than 1. Okay, that means that you are here in the complex plane, and you get just a circle there. Okay. All the complex numbers with modulus smaller than z, than 1. Sorry. Okay. Yeah, so if you take this random variable, then the generating function is a function defined on this disk that goes to C, okay, and is defined by g of z equals the expectation of c power x. Okay, and what is this? This is just the sum of the probability that x equals k times z power k. And this sum goes from 0 to infinity. Okay, so it's a power series. Okay, it's a series of powers of z. Okay, so just to be very clear, this is just a polynomial in z. Well, it's a series, so it's a maybe infinite sum of powers of z, but it's a simple object. Okay, for example, 1 plus z plus 2z squared plus 1/3 of z cubed plus anything. Okay, it's just a sum, and the coefficients are probability, so it's numbers between 0 and 1, and this is classical series. Okay, and of course, since it's a series, you can talk about the radius of convergence, the domain of definition of the function, and whatever. Okay. Okay. Exercise. Sorry, do you have a question?
Yeah. Is it the z? Is it a lowercase or a capital?
Lower. Yeah. It's, yeah. Thanks. I'm trying to. I mean, I use both, so for lowercase. So I'm going to try to use the. So those two are lowercase, and this one is capital case. Okay.
Okay. Thanks.
Okay. So now a little exercise. Try to compute the generating function of a binomial random variable. Okay, what do you get if you compute the generating function of a binomial variable? Okay, so that's your exercise. Maybe we can take something quite simple. Okay, you take x, binomial distribution of, I don't know, 5, 1/2. Well, 1/4 actually. It's because 1/2 is a very particular case where you have numbers that are the same. Okay, and the first one who finished the exercise, you can just comment on the chat. I will know that you are advancing. Anyone knows where's Alexi? I see he's not online, but I don't know if he's okay. He was with you on the other lectures?
He was there this morning.
Okay. Okay. Okay, good. So do you have troubles computing this function, or is it, it's quite simple. The only thing you need is to say, okay, this generating function is a function on z, little z, sorry. C, and this is just the sum, okay, from k equals 0 to n, since after n this will be 0, since we have a binomial distribution, and actually I said that n was 5, so this is the sum from 0 to 5 of the probability that my random variable x takes the value k times little z power k. Okay. Now, what are the coefficients if I say it's a binomial of 5 1/4? Okay, so make just a table of values of range from 0 to 5. And I'm going to take in numerical values of that. Okay. So how can I take? Yeah, I know. Maybe a picture. Picture would be enough. Okay, so if you compute those values, you simply get 0.33 times z power 0 plus 0.39 times z plus 0.26 times z squared plus 0.08 times z cubed plus 0.01 power 4, and the last one is 0.0009 z power 5. Okay, was that clear? Easy for you all to find that number? Okay, so again, the only thing you need to remember is what's the value of the probability for a binomial distribution taking the value k. Right? This formula, you have to know it perfectly well. and then it's just a polynomial in this case, because after some value, after value k equals 5, the binomial coefficients are 0. So this sum actually stops at k equals 5. If we were in the case of a geometric distribution, you know that even if the value is getting closer and closer to 0, they are not 0. So you have an infinite series, okay? But it's almost the same. Okay, now why are generating functions interesting? Well, generating functions are nice because you can access to different moments of discrete random variables as the derivatives at 1 of any discrete distribution. Okay, so that's the result here in red because it's a very, very important result. We have a nice theorem, okay, that says that if you take this function, you compute the derivative of the function, and you evaluate the function at 1, okay, so you compute the derivative of j, and then you take z equals 1, well, that is actually just the expectation of x. Okay, so there is a link between the derivatives of the generating function and the moments of the random variable. And if you continue differentiating this function, for example, here you get the second derivative of j at 1, this will be equals to the expectation of x times x minus 1, okay? And of course, you can get access to higher order moments if you continue to derivate this function, okay? Any questions on that? No. Okay, so I have my schedule here. Let me just check something. Okay, so our next class is on Tuesday, 23, and Wednesday, 24. Okay, so as I told you before, I think you will have a little exam on that for that date. I'm looking for the email I sent to you. Test, maybe. Do you remember when I said it was your test?
March 24.
Yeah, I think it was in March, but it's scheduled.
Yeah, March 24. So on February 24, you have the list of exercises. Yeah, that's the thing. Okay, so on March 24, so it's in 2 weeks, you will have a list of exercises to try. Okay, so it's not an exam, but during the 3 hours of lectures, you will be alone. Of course, you have access to the notes. You can have access to the internet. We don't expect that you know everything. We don't want you memorize things. The idea is that you will be able to solve problems, having time, of course, it will give you some time, and see what get out of that. Okay, so if you get stuck, it's not a problem. You just have to continue to try to understand what happens, how to do computations. So please note that on March 24, you will have a list of exercises, and you have to try to do it, and then you will send the things you wrote to me. Depending on, I mean, if you prefer to use pencil and paper, it's okay. You can just send me the pictures of the things you did, and I will send to you a correction later. Okay. Okay, so just remember that on February 24, you will have this 3 hours time for exercises. Okay. And at the end of the time, just send me the things you wrote to see if you understood well or not the notions. But it's not, you won't have a mark for this. Okay, so next we have lecture on.
Sorry. Did you give the answer about the last exercise? How much it was? Yeah, did you give it? Can you repeat it to me, please?
Yeah. That one, I think, no? So Albin has a question. Yeah, so if you want to write it on LaTeX, it's okay. It's perfect. Okay. So you must know. I mean, in my course, we don't have time to learn that, but you may learn that from yourself how to use LaTeX. Okay. LaTeX is the thing for write mathematics and all the serious papers on machine learning and artificial intelligence are written on LaTeX. So you have to know how to write and use LaTeX. Okay. At the beginning, it's of course it takes time. You may think it's not easy, but now everything has very it's very simple. If you use, for example, overleaf, that should be quite easy. Okay, so if I show you here the overleaf web page, yeah, here you can just say new project. I don't know, mathematics for machine learning, and just yeah, here you have your document, and on the right you have the PDF created after compilation, and here you can write any type of formula. Okay, so for example, you say I want a formula containing, I don't know, the expectation, you know, of x, which is defined as the sum over x.
So we can't see your screen.
You can't see my screen?
No, we have a black screen.
Oh, that's very weird. Okay. There.
Much better, yes.
So, you know, this is overleaf. You just select a document and then you can create a formula here. For example, this is the sum of x times the probability of x takes the value little x. You compile this and you get this formula here. Okay, so you need to know how to use LaTeX. Well, I get an error here. Undefined control sequence. Of course, that's because I don't use package AMS math and AMS symbols, I think. Okay. Any question on that? Okay, and I think we can finish with this little theorem. This theorem says that the generating function characterizes the distribution of a random variable. Okay. What does it mean that something characterizes the distribution of a random variable? That means that the information contained on that object is large enough to know everything about the distribution. So if you have a random variable x, we will see that some quantities characterize the random variable. The first one is the probability distribution function, which is simply know what's the value of the probability that x takes the value k. It's also equally equally enough, or I mean, you know, those are equivalent. So if you know one of them, you can know the others. The next one is the cumulative distribution function, which is the probability that x is smaller than little x. Okay, so if you know that one, you can know that one. They have the same amount of information. The other thing that will be large enough is the generating function g of z. This quantity also characterizes the law of the variable x. And another thing known as the characteristic function, which usually is denoted by phi, okay? And this is the Fourier transform of z, okay? Fourier transform of x. It is known as the characteristic function. So if you know any one of those four functions, then you know everything about x. Okay, you can compute expectations, you can compute variances, you can compute conditional expectations, everything. Okay, so I know we are starting the semester, so it's maybe not already everything clear, but I'm trying to give you some tools to have a look of the general domain of probability. Okay, so you have an equivalence on all those quantities. If you know this one, you can have this one, and this one. Okay, and any of those is good to know everything about the random variable. Okay, any last question before we leave? No? Okay, good. So yeah, you can have the notes. So don't wait just a second. I have to export the notes here. So lecture of February 17. Take it on the chat, okay? I'm sending the lecture on the chat, and tell me if it's good for you, okay? So it's 18 pages document. It's just uploading on the conversation. Okay. Why is not finishing this thing? Okay, chargement en cours. Just be patient. The YouTube link is updated. I mean, after every class. So if you want to see again the lecture, just go directly to the channel. It's I upload directly after the lecture the video. Okay. Yeah. So there you go. It's sending. Any other question? Is it good? Okay. Well, have a nice afternoon. If you need anything, I will be here. Okay. Bye bye. Have a nice week.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye bye.
Thank you.
Thank you. Bye.
Thank you. Bye.